Hello students, let us continue our discussion on electrochemical equilibrium. So far we have seen the application of the concept of chemical potential to electrochemical equilibrium, and today I will go a little beyond what we have discussed so far and look into the numerical application of the principles that we have learned so far. So, once again I am going to stick to very simple concepts and very simple numerical problems. So, let us have a look at our first problem. So, almost all of you have seen this schematic diagram of a Daniell cell before. This is from your high school days. So, what do I have here? I have two different compartments. On the left hand side compartment, I have zinc sulphate solution in water, and this has been represented here as ZnSO4 aqueous. In this solution, a rod made up of solid zinc is dipped, and this is connected to a platinum wire, which I represent here by writing PTL solid. Now, why do I write L? It is a platinum wire, therefore, it is in the solid state, but that subscript L tells me that this platinum wire is connected to the left hand side compartment of the Daniell cell. Now, let us focus our attention to the right hand side compartment. So, what do I have here? I have an aqueous solution of copper sulphate present in this compartment, in which I have dipped a copper wire. So, this copper wire now is represented as copper solid. So, if I compare it with the left hand side compartment, I have a zinc solid wire or a piece of zinc solid dipped in zinc sulphate solution. On the right hand side, I have a solid copper wire or a piece of solid copper dipped in aqueous copper sulphate solution. And here again, just to complete the circuit, I have attached another platinum wire, but since this is connected to the right hand side compartment, I have used this notation PTR. And we have already seen how to write down the entire circuit and under what condition, in the presence of a salt bridge connecting the two electrolyte solutions, we will be able to drive electromotive force through an external circuit. So, in this particular situation, the first problem is a kind of a review problem. So, I am asking you to set up the Nernst equation for the Daniell cell. So, all I will have to do is I will have to look up the structure of the Daniell cell, and from there go step by step from the elementary knowledge of the half cell reactions to the Nernst equation. So, what should be my first step? Of course, this is the cell schematic diagram, but I can have a shorthand notation for the cell diagram as follows. So, what I have here is this is the left hand side platinum wire, which is connected to a zinc solid, and then this is dipped in the aqueous solution containing zinc 2+ ion. Now, as discussed before, the double line over here that represents the presence of this salt bridge connecting the other electrolyte solution containing aqueous copper 2+. And this is in contact with a solid copper, which in turn is connected to the right hand side platinum wire. So, this by the standard convention is the cell diagram. So, can I now write down the half cell reactions? So, let us write down the half cell reactions in the convention of reduction. So, when I have copper 2 plus aqueous, it can accept 2 electrons, then get converted to copper solid. And the standard data tells me that there will be a standard reduction potential for this half cell reaction, and I know from the standard data table this is plus 0.34. Now, if I look at the second half cell reaction, then I find that I can have another reduction reaction Zn2 plus in the aqueous medium, upon accepting 2 electrons goes over to zinc solid, and the associated standard reduction potential for the pair zinc 2 plus to zinc, that is given by minus 0.76 volt. So, here if I want to check what kind of reaction I will be having in the cell, I will follow this notation, that reduction at cathode on right. So, what will happen is, on the right, that is here in this compartment, there will be a reduction reaction whereby copper 2 plus in the aqueous medium will be reduced and get converted to copper solid. Okay. Now, what will happen to the left hand side compartment? Obviously, there will be oxidation at anode on left. So, this is the convention that we are going to follow in accordance to the standard notation of electrochemistry, which is practiced these days. Reduction on the right, and reduction happens at the cathode. So, what I will do is, now I will write down the reduction reaction, and I say that the E naught value on the right, that is equal to plus 0.34 volt. Now, oxidation on the anode on left, I will still retain the reduction reaction, as you will see how I am going to handle it in the next step. So, I will still retain the reduction reaction because I am using the standard reduction potential for this pair, that is Zn2 plus Zn solid. Now, in order to write down the net cell reaction, what I am going to do is, I have to reverse the reduction reaction for the anode, because at the anode we have oxidation. The way to do it is, I add negative signs over here, basically implying that I am taking this equation and deducting this equation from the first one. So, what do I get? I get as the net cell reaction that copper 2 plus aqueous, which comes here, that gets converted to copper solid, and upon reversal I have zinc solid that is now undergoing oxidation, and it is going into the aqueous medium in the left hand side compartment as Zn2 plus. And this notation actually helps us, because now I can very easily write down that the E naught cell is equal to E naught R minus E naught L, where I am using the convention that each of the E naught values are the standard electrode potential for the electrodes or the half cell reactions at each electrode that I am writing down. So, this is the very first step in setting up the Nernst equation for any cell. So, you have to have the cell diagram which is appropriate for the given cell. Then you will have to write down the half cell reactions in the form of reduction, so that you do not have to change the sign of the E naught values. Then you use the convention that reduction on the right and reduction at cathode. And then what will happen is you will have oxidation at anode, and you can write down the net cell reaction, and immediately the standard cell potential is going to be the standard reduction potential of the electrode on the right minus the standard reduction potential of the electrode on the left. Now, that here I am basically retrieving by adding another negative sign over here. So, now from the given values of the standard electrode potentials E naught L and E naught R, I can go ahead and find out E naught cell as E naught R minus E naught L. So, if I put in the values, that would be plus 0.34 volt for E naught R and minus 0.76 volt for E naught L. But as you see, there are two negative signs over here. Therefore, essentially I will be adding up 0.34 volt and 0.76 volt, and the answer would be E naught cell is equal to plus 1.1 volt. So, now that I know the net cell reaction, I also note another important information that I get by writing out the half cell reactions and the net cell reaction. So, what I have here is when the reduction is happening at the cathode. So, there the copper 2 plus ions are accepting 2 electrons from the electrode over here and depositing solid copper. Okay? That means that this region I have transferred 2 electrons. Similarly, when I look into the oxidation at anode, I see that there the solid zinc will leave 2 electrons on the electrode and go into the solution at Zn2 plus. So, what is the number of electrons transferred for the net cell reaction? 2 on the right and 2 on the left. So, that number n, that is equal to 2. So, in addition to the E naught cell, I now know the number of electrons transferred for the net cell reaction. Now, moving ahead, I now know the standard cell potential, I know n equal to 2. Therefore, I can very easily write down the Nernst equation for the cell potential. So, the cell potential will now be given by the standard cell potential minus R, that is the universal gas constant, multiplied by the temperature at which you are measuring the cell potential, divided by NF. So, what is N? N is the number of electrons transferred to achieve the net cell reaction. F is the Faraday constant. And then I have taken a logarithm of what is known as the reaction quotient. So, what do I have on the top? I have on the top contributions coming from the products of the net cell reaction, and in the denominator I have contribution coming from the reactants. So, following the discussion of chemical equilibrium, for this electrochemical equilibrium, I am using the activities of each species appearing in the electrochemical equilibrium reaction over here. So, the first term is the activity of solid copper, the second term is the activity of zinc 2 plus in the aqueous medium. In the denominator, I have activity of zinc solid multiplied by activity of copper 2 plus aqueous. We have already learned in the class on chemical equilibrium that there are some standard values that we accept for activity. According to that, I know that for a pure solid phase such as the ones I see here for copper solid and zinc solid, the activities, the respective activities would be equal to 1. Correspondingly, I find that this is the Nernst equation for the Daniell cell, whereby I have used the I can use the value of E naught cell over here. I am using the value of n here, which is equal to 2, and in the logarithmic term I have a ratio of activity of zinc 2 plus aqueous divided by activity of copper 2 plus aqueous. So, this is how we set up the Nernst equation for the Daniell cell. But here there are a few things that I would like you to note down. Therefore, what happens is I can always put in the, if I know the E naught cell and if I know the concentration at which the zinc sulphate solution and the copper sulphate solutions have been taken, and if they are very dilute, I can replace the activities by their molality or molal concentration. So, in that case, depending on the experimental setup, you can very easily go ahead and compute the cell potential for this particular cell. Therefore, E cell is dependent on the concentration of the zinc sulphate solution and the copper sulphate solution taken to construct the cell. Now, this brings me to the final another useful expression, that is R T by F. This is a constant at a given temperature. In general, this is 25.7 millivolt at 298 Kelvin. If that is so, then you can rewrite the Nernst equation for the cell potential in this form, where I am expressing E cell, that is the cell potential, in units of volt, and for this particular cell I have on the right hand side, this is a contribution coming from E naught cell. This is the term which corresponds to R T by 2F, and then logarithm of activity of zinc 2 plus aqueous divided by activity of copper 2 plus aqueous. But you must remember that this particular value is valid at 298 Kelvin. But most experiments, they employ this temperature because that is a normal room temperature in a wide variety of cases, and therefore, this equation can be directly used to find out E cell as a function of concentration of the two solutions given here. Now, moving ahead, let us have a look at this particular problem. I would like to estimate the equilibrium constant for the following electrochemical reaction, but once again I am employing an experimental temperature of 298 Kelvin. Now, what is the electrochemical reaction that I am looking at? I have an aqueous solution of permanganate, which is interacting with an aqueous solution of oxalic acid in the presence of acidic medium, converting the permanganate ion to Mn2 plus aqueous and producing water and releasing carbon dioxide gas. So, this is the balanced chemical equation, and here I want to know the equilibrium constant if this reaction is carried out in an electrochemical cell. Now, there are additional data which are given to you. So, in this case, as you see that the permanganate ion in which Mn is in the oxidation state of +7 is getting converted into Mn2 plus. Okay. So, I would say that this is a reduction reaction. Similarly, in carbon dioxide to oxalic acid, this is also a reduction reaction, and I find that the standard reduction potential for these two redox pairs are plus 1.51 volt for permanganate to manganese 2 plus, and it is minus 0.49 volt for carbon dioxide to oxalic acid or the oxalate anion. So, in order to estimate the equilibrium constant, I know that my starting point once again would be writing down the half cell reactions. So, what is the half cell reaction that I am talking about? MnO4 minus aqueous plus 8H plus aqueous can take up 5 moles of electrons. So, 1 mole of permanganate in the presence of 8 moles of H plus ion in the aqueous medium can take up 5 moles of electron, producing 1 mole of Mn2 plus aqueous plus 4 moles of liquid water. And from the given data, I know that the standard reduction potential associated with this half cell reaction is plus 1.51 electron volt. Now, let us have a look at the second half cell reaction. So, here carbon dioxide, 2 moles of carbon dioxide in the gas phase in the presence of 2 moles of H plus ion in the aqueous phase can undergo a reduction with the uptake of 2 moles of electron, producing oxalic acid in the aqueous medium. Now, I am not writing down oxalate anion and 2H plus, that is simply because oxalic acid is a weak electrolyte, and therefore, I am retaining its net composition, knowing that it will be only partially dissociated in the medium. Now, the standard reduction potential for this redox pair is given as minus 0.49 volt. And once again, I am going to use the notation that reduction at cathode on right and oxidation at anode on left. Now, look at the net cell reaction. I find that in the net cell reaction, permanganate is getting reduced to Mn2 plus. Okay. So, it means that here this couple has a much higher standard reduction potential, and therefore, they are more likely to undergo the reduction reaction. And this has a much lower standard reduction potential, therefore, they are less likely compared to this pair to undergo the reduction reaction. So, if I now write down I want to write down the net cell reaction, I understand that I must balance out the number of electrons exchanged while counting the net cell reaction. Here 5 electrons are needed, here 2 electrons are needed. So, what I will do is I will multiply this equation by 2 and multiply this equation by 5. So, that way my half cell reactions look like this. So, reduction at cathode, it is 2 moles of permanganate ion in aqueous medium reacting with 16 moles of H plus ion in the aqueous medium and taking up 10 moles of electron, giving rise to 2 moles of Mn2 plus aqueous plus 8 H2O liquid. Similarly, the oxidation at anode now involves 10 moles of carbon dioxide gas. Actually, this is a reduction reaction that I am showing with 10 moles of H plus ion would take 10 moles of electron to produce 5 moles of oxalic acid. So, if I want to show the oxidation at anode, I will just use a negative sign over here, and the net cell reaction would be this equation minus this equation, and that will be this reaction that I have shown here, which is given to me. So, now I understand that I can find out the standard cell potential of by coupling these two half cells. And how do I do it? The first thing I note is For the net cell reaction, I find N is equal to 10, and not only that, the standard cell potential is now going to be E naught R minus E naught L, where these values are given to you. So, what is E naught R minus E naught L? That is 1.51 volt minus of 0.49 volt. That gives me the standard cell potential as 2.0 volt. Now, what I have here with these information, I can estimate the equilibrium constant. Why? Because we know that E naught cell is RT by NF logarithm of K equilibrium. Therefore, if I am using this log to the base E expression, I can find out K equilibrium is exponential of NF into E naught cell divided by RT. But many of the times, as in this particular case, an alternative expression is found to be useful. So, if E naught cell is expressed in the units of volt, I can use this expression where N is the number of electrons transferred, but instead of the natural logarithm, now I am using log to the base 10. And I am going to use this expression here, and therefore, K equilibrium is going to be equal to 10 to the power of N E naught cell divided by this number 0.0591. Now, this number is in volt, therefore, I will have to give the value of E naught cell in volt, and accordingly I will find that the equilibrium constant is turning out to be 10 to the power of 338. So, in this lecture what we have seen is the basic exercise for the application of any electrochemical equilibrium is that you must be able to write down the half cell reactions, write down the net cell reaction, then identify the number of electrons transferred in order to arrive at the net cell reaction starting from the half cell reactions, identify whether you have reduction on the right and reduction at cathode, oxidation and anode, and calculate the standard cell potential from a difference between the E naught right and E naught left. And then you can go ahead and calculate the equilibrium constant for the electrochemical cell reaction, and you can also find out the cell potential provided you know the activities of the components of the cell. Thank you.